Finished last 45 minutes by interpreting a little bit about the results of single letter probability for QAM and compare that with PAM. And we came to the conclusion that if we can use QAM, so is that preferable to pulse amplitude modulation? Yes. Now, then there was also this question about previously that we had, what is the symbol error probability and bit error probability? How does that differ between the different constellations and so forth? And actually, this gray coding trick that we do for PAM, we can actually do in 2 dimensions also. So if we want to look how to do that, the idea here is that we have now a 16 QAM constellation here, and we need to put out bit patterns along in this, 4 bits per point. And what we would like to do with that is that if I go look at the bit pattern of this point, the immediate neighbors, that is, if I go to the right, I go up, go to the left, or go down, I'd like the bit patterns only to change in one position. Because then if I make an error and go to this adjacent symbol, I will make 1 bit error. That is, 1 out of 4 will be wrong, but the other 3 will be correct. Okay, so that's the idea here. And to do that, we just do a gray code along that axis. It's a 2-bit gray code because we have 4 points along this axis. We do a 2-bit gray code along that axis. And for each point, we take 2 bits from this one and 2 bits from this one and just build up the 2-dimensional gray code like that. So the first point here would be 0, 0, 0, 1, 0, 0 from down here, and 1, 0 from here. So the first row here, all of them will end in 1, 0. So 0, 0, 1, 0, ends in 1, 0, ends in 1, 0, ends in 1, 0. So ends in 1, 0 along that axis. And the first 2 bits follows this gray code. And then it's clear, since this is a gray code, the red thing is a gray code, then the first 2 bits which are changing according to gray code. So they will only differ in 1 bit. Right? And then if we go down from here to here, the only thing that we changes is along a gray code along this dimension, which means that we only differ in 1 bit between adjacent points in the vertical plane here. Right? So from 0, 0, 1, 0 to 0, 0, 1, 1, we only change 1 bit. Here only changes 1 bit, only 1 bit, only 1 bit. Okay, and then we just fill out the rest. And boom, we have a 2-dimensional gray code. So that was not very hard, actually. Yes, okay. So that's about it for the physical layer. So remember that the physical layer, what it is trying to do is trying to transmit bits over a channel. And to do that, we need to convert the bits into a waveform which is suited for the channel. And at the receiver, we need to do the inverse. Take a signal and convert it into bits. And what we'd like to do is to minimize the number of bits that are in error in this. That's one thing that we would like to achieve. Then we also want to be power efficient and energy efficient at the same time. So to get down the symbol error probability and bit error probability is important. And we can do that by playing around with bandwidth and power. However, at the end of the day, any physical layer will eventually, every now and then, make an error. Maybe the symbol error probability is 10 to the minus 3, meaning that 1 symbol out of 1,000 on the average is error. Or it could be significantly higher or lower, depending on the physical layer we have. Actually, for wireless transmissions, the symbol error probability is quite high, due to engineering. It is a smart engineering thing to do that. It's not obvious at all now that this would be smart, but it's actually the solution we have. So then we will have errors in the transmitted bits. So what do we do then? Well, we need to deal with this. And this is the purpose of, for instance, the data. So we have the physical layer at the bottom, and the layer above it is the data link layer. And what the data link layer is doing, among other things, is to do error detection or error correction, or some combination of error detection and error correction. So we will start to talk about error detection. And error detection is done through coding. Now we're not talking about writing computer code here, it's codes in this specific meaning. So what we want to do is we want to protect the data when we transmit that over the channel, or rather we want to prep the bits that we transmit over the channel so that the receiver can figure out whether errors have occurred or not. Okay, so that's the objective now. And to do that we use codes. And one important class of codes is called binary block codes. And binary just means that there is binary input and binary output. Block means that we look at a block of bits as the input, and then we have a block of bits in the output. Okay, so binary block codes. So if we look at the left here, we have a number of bits, B0, B1, up to B subscript k minus 1. So we have k bits here. And for each such input block, D, which is called also the information word. Okay, so these are called the information bits. This is what actually carries data information. And if we block k of those bits into a vector, then we call this an information vector, or an information block, or an information word. It's the same thing. It's a block of bits. And then we feed this through this device that spits out a number of bits. And the number of bits out is actually small n here. And for all practical all practical block encoder, n here is greater or equal to k. So it outputs more bits than the input. Okay, we see that this is actually crucial for this to work. So these bits, the C bits here, are called code bits. And the block of code bits is called the code word, and it's of length n. Since we have a finite number of possible input patterns here, namely we have 2 to the power of k possible inputs, right? We have k bits. How many patterns of k bits are there? 2 to the k. Okay, which means that and also this block encoder is a deterministic device, so it does the same always. So for each input there is an output, and since there are 2 to the power of k possible inputs, the number of possible outputs is also 2 to the power of k. And for reasons which will become obvious, we never map 2, or very seldom map 2 different inputs to 2 different outputs. So we have 2 to the power of k distinct outputs, different bit patterns here. Okay, the collection of all possible outputs, C1, C2, up to C subscript 2 to the k, this is the set of all possible code words. This is known as the code. So the code is the set of all code words. And then there is something called the code rate, which is the ratio between k and n. So the ratio between the number of input bits to the number of output bits. And typically n here is larger than k, so the code rate is a number less than 1. And the interpretation of this is that it tells us how many information bits there are per code bit. Okay, so if we have, say, 4 input bits here, say that k is equal to 4 and c is equal to 6, then we know that each code word here carries exactly 4 bits. Right? Because for each 4-bit pattern there is a code word out consisting of 6 bits, but it carries only 4 code bits. Okay, and in this case the code rate is 4 divided by 6, or 2 divided by 3, 2/3 in this particular example. Okay, so let's have a look at this. a small example might illuminate what's going on. So a simple example, the input to the block encoder is this this information bit word. And suppose it's a 2-bit word, so it's 0, 0, 0, 1, 1, 0, or 1, 1. Okay, so these are the possible inputs. And now we need to define the block encoder by, for each possible input, say what the output should be. And the output is C. So if the input is D, the output is C. Okay, and suppose that we have 4-bit outputs. So for the first 0, 0 input, the output happens to be 0, 0, 0, 0. Okay, and for the second input, 0, 1, the output is 0, 1, 1, 0. I don't know, I'm just making this up. Okay, so for input 1, 0, the output is 1, 0, 0, 1. And for the last possible input, 1, 1, the output is also 1, 1, 1, 1. So the number of input bits here is k equals 2 in this case. The number of possible inputs is 2 to the k, 4 in this case. And therefore the number of code words out is also 2 to the k equals 4. However, the number of output bits here is not specified by the input. It's a design choice, and here we have selected that to be 4. Okay. But the number of code words is dependent on the length of the input. However, the length of the output is a design choice, and it's a design choice. So in this case, we have that the code rate RC is 2 divided by 4, which is 1/2. Okay, the code, curly C, is the set of all code words. So it's a set of what's in this right-hand column here. So it's the first code word is 0, 0, 0, 0. Second code word is 0, 1, 1, 0. Third one is 1, 0, 0, 1. And the fourth and final one is 1, 1, 1. Like this. Questions? No. Okay, so let's go back then. So an NK block encoder is something that takes K input bits and spits out N code bits. A block of input bits is called an information word, information vector, or information block. The output is called a code word, code block, or code vector. Same thing. And inputs and outputs are binary. Okay, so what use are these? Well, first of all, let's take this generic construction and make it a special case. And this special case is what's actually used in practice. Okay, so that's why we're talking about it. And that is when these block codes are systematic. And systematic means that the following. Remember that the input is the set of input bits, or input word D, and the output should be a code word. A systematic code simply copies the information bits and put that as the first bits in the code word. And then there are some check bits or parity bits following it. So a systematic code word have code words of the following form, that the mth code word or a code word, whatever code word we're looking at, consists of the corresponding input bits to that code word, followed by some check bits. And these check bits is a function of the input bits. So a block diagram here is that D is then going through this check bit calculation block and outputs the check bits, which corresponds to D. And this MUX multiplexer here simply takes D and then append P. So the output C is D appended with P. Okay. There are many advantages to this systematic block code. One thing is that we can immediately read off the information bits from the code word. Otherwise, in the general case, all the bits in the code word would be some possibly complicated function of the input bits. And then to figure out the input bits here, we need to potentially do a complicated inverse of that function. And it turns out that it's, of course, easier to do like this, and we could do that without any loss of performance, one can show. Okay, so going back to our example here, is this a systematic code? Yes, yes it is, right? Because if we look at the input bits here, those, we find them exactly here, like this. So it's a systematic block code. The other bits, so these, the parity bits here, if we look closely on them, they are just simply the input bits, but in reversed order. Okay, so that's a very, it's not a very good code, this, right? But it's just the way it's done like this. Typically, this is a more complicated function of the input bit. We'll see an example later on in this lecture. All right. So these bits then are sent, okay, so what happens then next? After this block encoder, so we have now the code bits. These are then sent to a pulse amplitude modulator, transmitted over the channel, and then we decode the bits. Okay, so how this looks, a block diagram on how this looks like could be something like, let's see how much space I have. Okay, so let's do it here. We have our information bits, and then it goes through an NK block encoder to produce the coded bits, C. Okay. Then C is sent through with some modulator, for instance PAM or QAM or what your favorite modulator is, to produce a transmitted signal, let's call it S. And then it goes over a channel where, let me move this a little bit, like this, okay, where we add noise to it, and then we have the receipt signal R of T here, and then we feed that through a demodulator, and the output of the demodulator is a guess on the input to the modulator. So here we have C hat. For reasons that will become, oh no, I don't want to do that, okay. Here we go. So we will actually not call this C hat, but rather Y, like this. And the reason for this a little bit clearer later on. But what we would like to do, we would like to transmit the coded bits over a channel and then decode the coded bits. We'll figure out which code word was transmitted. Everything which is inside from here to here, what is it? Well, there is an analog to digital, there is digital to analog converter in the modulator and an analog to digital converter in the demodulator. So from here to here is essentially a discrete channel. So we can draw this as follows. We have C here. And we can replace everything here with a simple addition of an error pattern to form Y. Okay. So the output Y is equal to the input C plus circle plus or XOR or modulo 2 addition with some error pattern E. So what does this mean? Well, it means that Y is a binary vector whose first element is the first bit of the code word, modulo 2 added to the first bit in the error pattern, E0. The second bit in Y is C1 plus E1, and we continue to do that until we get to Cn plus En, like this. And this O plus is modulo 2 addition. Or XOR if you like. So it means that 0, O plus 0 is 0. 0, O plus 1 is equal to 1. So this is no big surprise. 1 plus 0 is equal to 1. So what is actually new here? Well, the thing is that 1 plus 1 is equal to 0. So that's the big invention here. And by doing this, what we see here is that for each input C is then XORed with the error pattern. So whenever the error pattern is 1, then we will flip that code bit. So the error pattern, say an example of E could be 0101, then the positions where the error pattern is 1 tells us where the errors occur. So error positions. So if the error pattern is 0101, it means that the transmitted code word is the received bits is the transmitted code word, except in the second and fourth positions where these bits have been flipped. Okay. So here we also see that since there are 2 1s here, there are total 2 errors that happen in this transmission of this particular code word. Questions on this? It's rather important that we understand that we can write this block diagram as this block diagram, where the input C and the output Y is the same in both of these block diagrams. It's important that we understand that, and that E here summarizes everything that happens here from the perspective of which bits are received in error. Okay. So if we can say something about, if we specify E, we don't need to know anything about what's going on the channel. Okay. Why do we do coding? Well, we do coding for two main reasons. One is called error detection and one is called error correction. So let's start with error detection. So error detection is what is that? Well, given Y and knowledge of C. Okay. So if we observe y and we know the code, then we need to make a decision or a guess. We need to guess whether y is equal to the transmitted code word or if errors have occurred. Let me do that again. So we know the code, and if we look at y, our task is to figure out, have there been errors on the channel or not? Okay. That's the task. So given y and c, detect if errors have occurred. Okay. So that okay, so let me see if I can shift here. So what we want to do here in the block diagram is to look at y and then somehow decide whether there have been errors on the channel or not. So how can we do that? That's the question. So this is the main idea. If y is not in C, so y is not a code word, what should we say then? Errors occurred or errors not occurred? So we know that we transmit code words, right? If we receive something which is not the code word, what do we think? Error or no error? Error, of course. Has to be, right? Because we know that we transmit code words. We know that the transmitter is sending code words. We just don't know which one. But we know it's going to send code words, for sure. So if the received bits here is not a code word, that's what this means, then for sure we know that errors have occurred. So we say that we have detected errors. Okay, so that's the output. Okay. The other alternative is, of course, that y is a code word. Then we say that no errors are detected. Okay. So error detection conceptually is very, very simple. We look at the received word. We look at the set of code words, and if the received word is not a code word, we say error has occurred, or if y is a code word, we say looks fine, no errors, right? Is this a good method? Well, for sure, if y is not a code word, then errors have to have occurred, clearly, must have. Okay. However, if this is the case, that y is a code word, we're not completely sure that errors have not occurred. Because there might be a case where we transmit a code word and the error is such that it transforms this code word into another code word. That is, that y is a code word, but not the transmitted code word, but it is a code word. And we say, okay, it looks fine. So sometimes errors slip through the crack. Okay. And what we want to do then is, of course, to minimize the probability for this to happen, because this is really bad, right? That you go to your next step in the processing scheme and you say, okay, here are the bits, I think they're fine, I didn't see anything wrong with them, and they turned out to be bogus, right? So that's a bad thing, okay? So the good thing is with this method, we will definitely, when we say there is an error, there is an error. However, when we say there is no error, there could be an error. Okay. So let's make an example here. And we use the same code as before. So suppose that D is 0, 1. Then we know that the output, the transmitted code bits, is 0, 1, and then it's the reversed order of them. So it's 0, 1, 1, 0. Okay, we can just go back and see that this is the mapping that's done. Suppose the error pattern is, okay, so it has to be 4 bits, and it's 0 in those positions where there are no errors, and 1 in those positions where there is an error. So suppose it's 0, 0, 0, 1, okay, which means that there is an error in the 4th position. And this would then yield that the output y is equal to the input, and the input is 0, 1, 1, 0, where we flip the 4th bit. So the output would be then 0, 1, 1, 1, right? So the error occurred here, because that's what the error pattern has indicated. Okay. So given this observation y and knowledge about the code, what should the receiver say? Should it declare that an error has occurred or not? Well, essentially we need to look at this, or what we need to do is to look at this pattern 0, 1, 1, 0, 0, 1, 1, 1, and then go back to look at the code here and see, do we find 0, 1, 1, 1 among the code? Oops, I did not want to do that. Okay. Do we see 0, 1, 1, 1 among the code words here? No, we don't. There is no such code word. Therefore, we're sure that an error has occurred. And we know actually from the example that the error has occurred. However, the receiver, of course, had no idea about this. Okay. So y is not a code word, which means declare error. Okay. Now suppose we that the error pattern is 0, 1, 1, 0 instead, which means that the output y is 0, 0, 0, 0. Right? The errors occurred here. Okay. Is y 0, 0, 0, 0, is that a code word? We can go back and check, but I can already now say it is, right? So we declare no error. Okay. So here we say that, okay, this looks fine. This looks fine because what I see is a code word. Okay, me as a receiver, of course, have no idea what the error pattern was, but it looks fine. So here is a problem, because what we have said that y is fine, no errors, even though that there are errors. Okay. So this is a problem of so-called undetected errors. So it can be shown in this case that these patterns 00110, 1001, and 1111 are undetectable. Error patterns. Okay. All other error patterns we can detect, but there are three that we are unable to protect ourselves of. Okay, so there are 16 possible error patterns, one there is no error, but out of these 15 that are real error patterns where we have one or several error patterns, there are 3 of them that we cannot protect ourselves with using this code. Okay. The other codes that we use in practice are much, much better than this example. Okay. So let's go back then to our systematic block codes here. So if this is the encoder, the way to do error detection here, it looks complicated, but the idea is very, very simple actually. Here we don't need to scan the big code to figure out whether the received word is a code word or not, because actually in practical codes the number of code words could be more than the particles in the universe. Okay, so it's a very, very large table to search through if we want to do that. So that's one reason why systematic codes are used. Okay, so we have a systematic encoder here. So C here is a systematic code word, meaning that we have the information bits first and then the check bits. And then we transmit that over a channel and then we get an output Y. And Y is the sum between C and the error pattern. So we split up the error pattern in 2 parts, one which affects the data bits and one which affects the check bits. So Y here has 2 parts, one which is corresponding to the data bits and one which is corresponding to the check bits. In the best of the world, ED and EP is 0, so then Y is equal to DP, which is what we transmitted. Okay? But there might be some errors in D and there might be some errors in P. So how are we going to check whether this is a valid code word or not? Well, there's a very simple idea, is that we take the first bits here and we compute the check bits which corresponds to this and compare them with the last bits. And if they are the same, then this is a code word. If they're not the same, it's not a code word. So what we take is Y here and we split it into the 2 parts, one which belongs to the data bits and one which is the parity bits or check bits. And then we take the data bits, the supposed data bits, and we do the same type of calculation of check bits that we did in the encoder. And then we get out check bits which corresponds to these bits. And if these check bits are equal to the check bits that we actually received, then we know that this plus this is a code word. If they're not the same, then we know that this plus this is not a code word. So you basically compare this bit pattern with this bit pattern, and if they are the same, then we think it's fine. If they're not the same, we declare an error. So, questions? Okay. So to check whether the received word, so to check whether these bits is a valid code word, what we need to do then is to see whether these check bits corresponds to these data bits. That's the idea. So how to do that is to calculate the check bits that corresponds to these bits. That's a well-known function. And then we just compare those the check bits which corresponds to these bits with the bits that we actually received. Okay. So that's the error detection mechanism here. Was that clear or unclear? Somewhat clear. Okay. look at it a little bit, and then you can figure out that this actually works, right? And it works regardless if the errors are in the first part and in the second part. Okay, it doesn't matter. Okay, let's do this. So let's figure out how to construct good codes for this purpose. And to do that, we need to talk about something called Hamming weight and Hamming distance. And Hamming weight and Hamming distance is like norm and distance we talked about earlier for signals, but now we're talking about bit patterns instead. So the Hamming weight is simply the number of ones in a binary vector. So W for weight, H for Hamming of some bit pattern U is the number of ones in U. Okay, so the Hamming weight for 0, 1, 1, 0, 0, 0 is equal to 2. Right? There are 2 ones in this. If we have this, which can be thought of also as the length of this binary vector, then we can compute the Hamming distance between 2 binary vectors, and that's simply the weight. Okay, so let's define what it is. It's the number of positions in which these patterns differ. So the Hamming distance between U and V is the number of positions in U and V where they differ, okay, which is equal to the weight of U plus V. So, for instance, if U is 0, 1, 0, 1, like this, and V is equal to 0, 1, 0, 0. So what is the Hamming distance between these 2 vectors? Well, we see that the first position is the same, second position is the same, third is the same, but they differ in the fourth. Okay, so from this we know that the Hamming distance between U and V is equal to 1. Okay, if we look at U plus V, we take the element XOR of this, then that is equal to 0 plus 0 is 0, 1 plus 1 is 0, 0 plus 0 is 0. Okay, so it's a 0 as long as these 2 bits are the same, and then it's 1 in the positions where they are different. Okay, and the Hamming weight of U plus V is equal to 1. Okay, so to compute the Hamming distance, what we take is we take the difference, which is the same as taking the addition of U and V, and then calculate the Hamming distance of that. Questions? No. Okay, so why do we do this? Well, we do this because we want to figure out what is a good code, and it has to do with the Hamming distance between the code words. Okay, so suppose we have some code with 4 code words like this. It just happens to be in some binary space of, say, I don't know, 16 dimensional binary space. I don't know how many bits there are in C, but there are 4 of them at least. Then I can find something called the minimum distance of the code, which is the minimum distance between 2 unique code words. So I compute the distance between all code words like this, and then find the minimum one. So we see here that C3 and C2 are the closest ones, right? So the minimum distance is the radius of the sphere that I can put in binary space, which goes from one code word and then barely touches another code word. Okay, so that's the smallest sphere I can do for this. Okay? So why is this good? Well, it tells me that if I transmit C2, then we have some error pattern. So the received word, Y, would be the sum of C and E. And the error is detectable. This E is detectable if, and only if, Y is not the code word. Okay, so what is Y? Well, Y is C plus E. So C plus E is Y. So that cannot be a code word, and that should be true for all code words. So it doesn't matter if I send C2, C4, C1, or C3. if this error is such, then I should not get another code word like this. So this error pattern is clearly detectable, right? Because I cannot go from one code word to another by just adding it to one code word. So here we see something interesting, is that if we take this sphere and we put that around all code words, then we see as long as the error pattern is confined to the sphere, it's a little bit inside the sphere, not completely on the border, but one step in, then it will never reach another code word. Right? So if the Hamming weight of the error, that is how many steps we go away from C, is less than the minimum distance, then E is detectable. Right? Because then the error we go can never really fully reach another code word because we're inside this sphere of radius d min. Okay. However, if the Hamming distance is greater or equal to the minimum distance, then the error might be undetectable, but not necessarily always. So for instance, this error pattern, this one, that goes, if C3 was transmitted, then this error pattern will be undetectable in this case, right? Because I can, if I transmit C3 and then I receive C2, and then I would say no error, even though C2 is not what I transmitted. Okay. However, this pattern here, this error, ED, is detectable because there is no way I can use ED to go from C4, C1, C3, or C2 to another code word. Okay. So the minimum distance constraint here that we put here just tells us what we can guarantee that the code can achieve, even though the code can be more powerful than what seems to be the case. Anyways, so from this, what would you say a good code would be? Should it have large minimum distance or small minimum distance? Large. Should have a large distance. And the rationale is that if there is a large minimum distance, the code words are separated by long distances, which means that it takes many errors to go from one code word to another. That is, we are robust to those. Okay, so we'll pick up the ball on Thursday. We're lagging a little bit, but you should be quite okay to do your projects now. For sure the PAM part, and now we're talking about the error detection part that you need in part 2 of the project. So I hope we will keep pace with your projects, and so you always have something to do.